Hello everyone. Today I'll be talking with you about the voltage of an inductor due to a forced current. So I have an ideal current source here, and it's going to force current through this inductor, and we're going to find VL of t, the voltage across the inductor due to the fact that we have a forced current through it. So again, for t equals less than 0, Is of t equals 0. So in other words, until we turn it on, it's going to be off. And for t greater than 0, when we turn it on, Is of t is going to be equal to 10 times t exponential negative 5t amps. That's the functional composition of Is of t. And again, we will seek to find VL of t for t greater than 0, which is when it's on. So first we'll start by taking notice of the fact that Is of t is equal to IL of t. It has to be because it's being forced through and it's in a series circuit. It can't be any more simpler than that. And next we'll take notice of the fact that VL of t equals L dIL of t dt, just for any inductor. And so that'll translate into Is of t, dis of t, dt. And so next we'll have VL of t equals L d dt of 10t exponential negative 5t. And we'll bring the 10 out in front. VL of t is now equal to 10L d dt of t exponential negative 5t. We're going to use the product rule here, and that evaluation gets us to t primed times exponential negative 5t plus t times exponential negative 5t primed. And so next, when we differentiate t with respect to t, we just get 1, and 1 times our exponential here is just going to give us our exponential. So we have exponential negative 5t, and then we have plus t, and then when we differentiate exponential negative 5t with respect to t, we'll get negative 5 times our exponential negative 5t. And so next what we'll do is we'll start simplifying here. Our 10 in the front times L. Well, L has a value of 0.1 Henry. 10 times 0.1 is just simply 1. So that'll go ahead and that'll disappear because 1 times anything is just what anything is. So now we have VL of t equals exponential negative 5t minus 5 times t times our exponential negative 5t. Next what we'll do is we'll go ahead and we'll factor exponential negative 5t out of this, and then that arrives us finally at an expression of 1 minus 5t times our exponential negative 5t. And of course the units for that are volts. So this is our final expression for VL of t, and what we'll do is we'll go ahead and we will use a circuit simulator, and we will plot this function versus what we get from our simulator. And of course we'll also check and make sure that we have consistency with Is of t as well in that simulator, and we'll make this functional composition and check the consistency of that as well too. So we'll go ahead and we'll do that right now. Okay, so for the simulation part of this video, we'll be verifying, confirming that what we got on the board was in fact correct. And so we'll go over our circuit here. General explanation of what we have is we have our 100 millihenry inductor. We have an initial condition of 0, which means no current is flowing in it initially. And we have our current source over here. I'm using a voltage controlled current source. This arbitrary function was not available, so I had to basically compose and make it up, and I use voltage sources for that with a multiplier. I multiplied those two together to get this up to this point on this end, and then over here on the right hand side, because I'm controlling current, then the forced current of the inductor would be 10 times t times exponential negative 5t. So we're going to confirm that first to make sure that in fact that is the case. So I'll just go ahead and copy my expression here and simulate this end of the circuit using the current probe. And so our simulation gives us this relationship. Now next, what I'll do is I'll paste in our mathematical expression and make sure that it matches up. In fact, it does. It matches up perfectly. At every point, you can see the red is overlaying the green throughout the whole entire time interval of 1 second. So that confirms it. So next, what we'll do is we will use a voltage probe, and we'll check the results of our derivation on the board for the voltage of the inductor, which is the result of forcing that current through the inductor. So I'll go ahead and simulate that, and our result is this. So next, what I'll do is put in our mathematical expression that we derived on the board here and see whether or not it matches up. And sure enough, it matches up exactly at every point on the curve. Again, the red, which is our mathematical expression, is overlaying our green, which is our simulation result, and we can see it matches up perfectly. So what we got on the board is in fact correct. And just one thing to notice about all of this here is that for our inductor, the voltage has changed instantaneously at time equals 0, which is characteristic of inductors, and also at 0.2 seconds, after 0.2 seconds, we have a reversal of voltage polarity across our inductor, which is also characteristic of inductors. So that will do it for our simulation verification portion of this video. Thank you for watching this video. Hopefully it was helpful, and have a nice day.